So the section 3.1 about piecewise functions is, that was a pretty isolated thing. We don't really, you see them just that one time, and then I'll try to throw in some problems sprinkled in there throughout the year to kind of keep you practiced up on the piecewise function stuff. But it's very different from the rest of Unit 3, right? The rest of Unit 3 is more about graphing functions than anything else, okay, and not piecewise functions. So what we want to do, the way this is going to play out in Unit 3, we're going to talk about how we can transform functions, like really basic, what we call parent functions, to look like more extravagant, extreme versions of those functions. For example, we could take something like an absolute value function or a quadratic function, and we could start with the most basic, vanilla, simplest version of each of those types of functions. And by tweaking the equation a little bit, tweaking the function, we could turn it into any kind of absolute value graph or any kind of parabola or any kind of line, for example, that we want to, right? By doing these series of transformations to it, okay? But before we can get there, before we can talk about how to transform these basic graphs, we have to know what the basic parent function graphs look like. So for today, that's all we're doing. We're just going to look at, I think it's like 8 of them, at 8 really basic but common functions that we use in algebra, and just talk about what those parent graphs look like. Okay, and that's your first assignment, is just all about that. It's just about memorizing what these graphs look like. Well, the first one is a line, and this is almost kind of a dumb one to even have on there, because we've already talked about lines, and I'll add this information, but with lines, it's not even really that important to think about them in terms of a parent function. They're so simple, we can just think about those as being in, for example, slope-intercept form and graphing them based on the slope and the y-intercept. But all the other ones, they're a little more complicated. And so with those, we do need to know what the parent graph looks like. Well, the parent graph for a linear function is just f of x equals the most basic possible line, which is just x, right? We know what that looks like. The line y equals x is just a line with a slope of 1 that goes through the origin, right? So we could fill in some information about this. What's the domain of this function? What's the domain of the function f of x equals x? What are all the possible x values that an ant could stand on? Go ahead and type it in chat. What do you think? Keeping in mind that line goes forever, down to the left and up to the right. What's the domain going to be of that function? All reals, yeah. It'd be all reals, wouldn't it, right? Every x value is contained on that graph. An ant could step on any possible x coordinate. There's no x coordinate he couldn't get to if he walked long enough, right? So this is all reals. What about the range? The set of y values. Everybody type it in chat. What do you think? If I projected that line onto the y-axis, wouldn't it cover the whole y-axis? So what's the range? Type it in chat, please. What's the range? Yeah, all reals, isn't it? Right? Everybody see that? It's all reals. If I projected this line onto the y-axis, it would shade the entire y-axis. So again, it's all reals. And the reason for that is, just another way to describe that, if an ant's walking along this to the left, right, along this line to the left, he's going to the left forever, but he's also going down forever, right? So he's going to hit all the possible negative y values down to negative infinity. If he walks to the right along this line, he's going to the right forever and up forever. So he's going to hit all the possible positive y values all the way up to infinity, right? Okay. End behavior. This is a new topic. You guys have probably never seen this idea before, but end behavior asks us what's going on way the heck out to the right and way the heck out to the left. There really are no ends to this function, but The end behavior means as x approach. Well, how do you think I would say this? If I want to go as far as possible to the right, I never get to the end, but what x value would I be approaching if I'm just going to go, without limit, I'm just going to go to the right. The ant's going to walk to the right on this function. What's the x coordinate that he's trying to get to, but he can never get there? But what is it? What do you think? What would x be approaching as the ant walks forever to the right? Anyone want to take a stab at that? What do you think, Ethan? How could we capture that idea mathematically that this ant is just going to go forever to the right, and we want to see what happens when he goes forever to the right? What value is he approaching? Say it again. Infinity, yeah. So as x approaches infinity, what a weird concept. What does y approach? What f of x is just a fancy name for y, right? What does y approach on this graph? If he's going to the right forever, what y value is he approaching? Okay, I'm seeing people drawing an infinity, right? It goes up forever, doesn't it? As the ant walks to the right forever, that's how we interpret this. As x approaches infinity, we interpret that as we're going right forever. Wouldn't we agree that the y value, f of x, is also approaching infinity, which we interpret as he goes up forever, right? Okay, now let's go the other way. What if we want to go to the left forever? What x value would we be approaching there, Gabrielle?
Can you repeat most of what you just said? I had to find my packet and I'm a little lost.
Oh, sure. So as the ant, as he went to the right forever, the way we can say that mathematically is x approaches infinity, right? Because the x value is going to get infinitely large. As he goes to the right forever, he's also going up forever, right? When he goes up forever, that means that f of x, which is just equal to y, is approaching infinity. Now we want to do something a little different. Now we want to see what happens when the ant goes to the left forever. So how would I say that? What's he approaching?
Negative infinity.
There you go, negative infinity, right? And that's our kind of our fancy way of saying left forever. And what's happening to the y values when the ant goes left forever on this graph? What are they approaching as the ant's walking along this graph to the left forever? Go ahead, Gabrielle. You can answer that one too.
Negative infinity.
There you go, negative infinity. Perfect. So as he goes to the right, or the left forever, he's also going down forever, right? That's how we interpret that. Okay, is this function continuous or discontinuous? Well, here's how you tell. If a function is continuous, it just means that I can graph the function without ever picking my pen off the board. If it's discontinuous, it means I have to pick my pen off the board at least once. Okay, so what do you think? What's the verdict? Continuous or discontinuous? Type it in chat, everybody. You can just type a C or a D. C for continuous, D for discontinuous. Yeah, it's continuous, isn't it? Yep, it's continuous. There we go. That's all we need to know. That describes that function. Okay, now let's look at an absolute value function. So this is the function f of x equals the absolute value of x. First of all, let's graph this thing so you can see what the graph looks like. So this has an interesting looking graph. It has a vertex at 0, 0. If we go over 1, we're going to go up the square root of 1, which is 1. If we go over 2, we're going to go, if I plug 2 in for x, f of x is going to equal the square root of 2, which is 2. And so you can see that this thing is just going like that, right? To the right. Okay, what about the other side? What if I go backwards? What if x is -1? If I'm plugging in a value of -1 into my function to calculate the y value, what's f of -1 going to be here? F of -1 is going to equal the absolute value of -1. What's the absolute value of -1? Type it in chat. Okay, I'm seeing it. People are holding up one finger. Yeah, it's 1, isn't it? Right? So I've got the ordered pair -1, 1. What if I plug in -2? Well, the absolute value of -2 is 2, right? And so on and so forth. And so we end up with something like that, right? So that's my absolute value function. It looks like a V. That's what the parent function for absolute value looks like. It's a V with the vertex being at the point 0, 0. And normally we would go over to the right and up 1. And so it's also going through the point 1, 1. Okay? All right, what's the domain of this function? What are the x values? If I projected that blue graph onto the x-axis, what x values are contained? What would that projection look like on the x-axis? Madeline?
Would it be 0, infinity?
Okay, so you're thinking about x values or y values?
I don't know.
Because the domain is the set of all the x values, right? So here's my x-axis. So if I projected that thing down onto the x-axis, so all those points would have to keep their x values, right? So if I projected this point onto the x-axis, for example, it's going to go down straight down so that its x coordinate is still 2, right? It would end up right there. And this point right there would go straight down so its x coordinate stays at 2, right?
Okay, so wouldn't the domain be -infinity to infinity?
There you go, -infinity to infinity, right? So the domain is all reals. And if we want to write that using interval notation, it would just look like that, wouldn't it? Okay. Now, what about the range, Madeline? Because I think you already thought about that one. What's the range going to be? If we projected this onto the y-axis, what's it going to look like?
0 to infinity.
Yeah, good. 0 to infinity, right? Because it contains a y value of 0 and every y value above that, but no y values below 0 are graphed. So the range is going to be from 0 up to positive infinity. Am I going to put parentheses or brackets around by that 0?
A bracket.
Yeah, a bracket. Very good, because it does include 0, doesn't it? Right? So we need brackets there. Okay? Good job. Okay, end behavior. Let's look at the end behavior on this. So as x approaches infinity, what does y approach in this case? As x approaches infinity, Devin, what does y approach? It does, doesn't it? Right? Because as we go to the right forever, we're going up forever, right? So that's also infinity. Okay, what if we want to go to the left forever? As x approaches negative infinity, what does y approach? Aidan McDermott? Positive infinity. Very good, right? Because as we go to the left forever, we're going up forever. Good job. Is this continuous or discontinuous? Let's see. Continuous or discontinuous, Carson? Remember what we're asking there. If it's continuous, it means I can graph it without picking my pen off the board. What do you think, Carson? Continuous or discontinuous? Continuous. Good job. Okay. So there's, and most importantly, the graph. That's the main thing, right? So there's the absolute value parent graph. Okay, what about a quadratic function? Well, quadratic function, the most basic one we can graph is just f of x equals x squared, right? So what's that look like? Well, we've got a vertex at 0, 0, and it's going to be a U-shaped, right? We get a parabola. It's going to go through the point 1, 1, and it's going to go, because, and we can check that, right? If I input a 1 into my function, the output is going to be 1 squared. Well, that's just 1. What if I input a 2 into my function? What's the output going to be? What's f of 2 going to be? Type it in chat, everybody. What's f of 2 going to be? F of x is x squared. What's f of 2? Oh, there we go. Good. It's 4. 2 squared. Good job. So f of 2 is 4. So we're going to go over 2 and up 4. Okay, so it's going to look like that. And what about the other side? Well, if I put in something like negative 2, negative 2 squared is also 4, right? So I'll go back 2 and up 4. I'll go back 1. F of negative 1, well, negative 1 squared is positive 1. And so there's our U shape, right? So that's what the parent graph looks like for a quadratic function. What's the domain of this thing? I want the domain, Lexi. What's the set of all x values? Okay, I'm seeing the universal symbol for the answer. Yeah, it's infinity. Good. Yeah, when you say infinity, you mean all reals, don't you? Right? It's all reals. What's the range on this one? What's the range going to be, Kinley? What's the set of y values that are graphed on our parent graph?
Is it 0, 1, 2? I mean 1, 4.
Okay, now those are the ones I graphed, but those are just convenient ones, but those are just 2 points of the infinite points that are used to make the graph, right? Those are just some key ones that help us graph it properly. Say it again. Yeah, there you go, 0, infinity. Very good, right? So it goes up forever, doesn't it? Well, we know that we have to have rounded brackets by the parentheses by the infinity. What goes by the 0 there? Brackets or parentheses? Brackets, good, because we include the 0. Good job. So what about the end behavior? As x approaches infinity, what does y approach, Olivia?
Is that infinity also?
Yes, it is. Okay, while you're at it there, Olivia, as x approaches negative infinity, what does y approach?
Negative infinity.
So think what that means. As x approaches infinity, that means as the ant is going to the right forever, he's going up forever, right? As x approaches negative infinity, as the ant goes to the left forever on this graph, is he going up forever or down forever?
He's going up.
Oh, okay, so that must be infinity then, right?
Yeah.
Okay, there you go. Continuous or discontinuous, Melinda? You can just type it in chat or say it, whatever you prefer. Aiden Bork? Continuous or discontinuous? Continuous. There you go. Good. I can graph that without picking my pen off the board. Okay, next one is what we call a cubic function, parent graph. That's going to be f of x equals x cubed. Okay, so let's just make a little t-table to get some points on this one, right? So we could pick if x equals 0, well, 0 cubed is just 0, right? So it goes through the origin. What if we pick 1? 1 cubed is 1, right? So we get the point 1, 1 over 1 up 1 cubed. What about 2? If I input a 2, what do I get back? Type it in chat. If I input a 2 into my function, okay, I'm seeing it. You need some more answers. What's the output if I input a 2 into my cubic function? Okay, good. It's 8, isn't it? Good. So over 2 up 8, unfortunately, that's off my chart, isn't it? So I'm going up 1, 2, 3, 4, 5, 6, 7, 8. So like way up there. And so I've got some key points here. I've got the point 0, 0. I've got the point 1, 1. And I've got the point 2, 8. Okay, so it's looking just like a steeper version of what we saw up here, right? On the right side. Okay, what about the left side? What if I input a negative 1? What's negative 1 cubed? Negative 1 times negative 1 times negative 1. Aha, I'm seeing it. It's negative 1, isn't it? Right? Negative 1 times negative 1 is 1, times another negative 1 is negative 1. So I got a point there. What if I plug in negative 2? Negative 2 cubed. Negative 2 times negative 2 is 4, times another negative 2 is negative 8. So over 2 in the negative direction, so over negative 2 and down negative 8. So right about there. So it's going to look like kind of like that, right? So there's our parent graph. Okay, what's the domain of this one? Domain of this one, Jonathan?
Isn't it all real numbers?
It is all reals, right? Because even though this gets steep, if I go, I can go infinitely far to the right or the left. I'm just going to be climbing or dropping really steeply is all, right? But it's still all reals. What's the range, Jonathan?
Isn't it all real numbers as well?
It's also all reals. Okay, as x approaches infinity, what does y approach, Muriel? What does f of x approach?
Would it be infinity?
It is, right? That's correct, because that means as I go to the right forever, as x approaches infinity, so I'm going clear out to the right infinitely far, what's happening to my y values? What's happening vertically? As I go to the right forever, I'm going up forever, aren't I? Okay. What about the other side of this? As x approaches negative infinity, so as the ant is going to the left forever, what's it doing vertically?
It's going negative infinity.
There you go. And is it continuous or discontinuous? There you go. Okay, good. All right, what about a square root graph? So now a square root graph, the most basic one we can have is f of x equals the square root of x, right? So what's if I input a 0, what's the square root of 0? Everybody type it in chat. Right, if I make a little t-table out of this one, if I input a 0, what's my output? Yeah, it's 0, isn't it? Square root of 0 is 0. Okay, so I get a point at 0, 0. What about if I input a 1? What's the square root of 1? If I input a 1 for x. Type it in chat. Square root of 1? Yeah, good, it's 1. Okay, I'm seeing it. So we get a 1. So I get another point up here at 1, 1. Well, what's another convenient value to input? Square root of 2 is some weird decimal. What's another convenient? 4. Yeah, good. What if I input a 4? If I input a 4 into my function, what's the square root of 4? Okay, good. So we're getting 2. So I've got another point over here at 4, 2. Okay, can I put a negative value in? Could I put like a negative 1 into my function? Can I take a square root of a negative number? I can't, right? Remember, that's one of my rules. I can't take a square root of a negative number and get a real answer, right? So this one stops. It has a starting point. It has a starting point at 0, 0, and then it just goes through the point 1, 1, and it goes through the point 4, 2, and if I went over 9, the square root of 9 would be 3, so I'd have the point 9, 3 if I kept going, right? Okay, so on this one now, what's the domain for this one? Riley Duchek, what's the domain? What's the set of all the x values that are graphed for my square root parent function?
Would it be foreign or I don't know?
Okay, so now remember, these points that we've just picked some convenient points on the graph, but there's an infinite number of points on this graph. Like I could pick 0.1. If I put in 0.1, I'm going to get the square root of 0.1, which is just some weird decimal, right? And I could pick values I could pick as big of values as I want to, but it looks like 0 is the lowest number we can put in, right? We can't put in a negative. You can't take a square root of a negative. So the domain is the set of all the x values. So there is actually a lowest x value this time. What is it? What's the lowest x value on our graph?
0.
0. Okay, and there is no biggest value, though. We can take a square root of as big a number as you want to. So what's the domain then? 0 to
Infinity.
There you go. Okay. And we know we have to always have parentheses with the infinity because we never get there. What about with the 0? Do I have a bracket or parentheses?
Bracket.
There you go, because I include 0. Very good. Okay, what about the range? While you're at it here, you got the hang of this, Riley. So what about the range? Is there some stopping point with the range, the y values?
Why no?
So look at the y. Okay, it goes up forever, doesn't it? The y values increase forever. Is there a lowest value of y?
Yes, 0.
Okay, good. So we're going to be the same thing, isn't it? It goes from the y values go from 0 to infinity. And again, I need a bracket there, don't I? Because I'm including 0. Okay. What about the end behavior this time? The end behavior is a little strange. As x approaches infinity, what does y approach? In other words, as the ant goes to the right forever, what are the y values doing here? Let's see. Who haven't I called on? Delaney Coiner. I haven't called on you, have I? Infinity. There you go. Good. So it's going up forever. So as x approaches infinity, y approaches infinity. Now, here's where it gets maybe just a little bit odd, though, right? I can't go any lower than 0, right? So the end behavior on the left, the lowest we can go is x approaches 0. And if x approaches 0, what does y approach? If an ant's walking along this function towards x equals 0, what y value is he going to end up at? Go ahead, Delaney Coiner.
0.
0. Yeah, there it is, right? And would everybody agree that this is continuous? Because once I put my pen down on the board at 0, I never have to pick it up again. Okay? Cube root. So that's f of x equals the cube root of x, right? And let's put some values in here. Now, this one's just a little bit, you're probably not as familiar with the cube root. But let's put in the value. If I put in 0, the cube root of 0 is just 0, right? So we've got a point here at 0, 0. What if I pick a 1? Well, the cube root of 1 is just 1 because 1 cubed is 1. So it goes through the point 1, 1. what would be the next convenient point? I can't pick 4 because the cube root of 4 is some weird decimal. What's the first number that above 1 that has a convenient cube root? 8. Good. Cube root of 8 is what? 2. Good. Okay, because 2 cubed is 8. Okay, so if we input an 8, if I input an 8, I output a 2. Okay, so I got to go over 5, 6, 7. So that's about right there, let's say. So I've got points 0, 0, 1, 1, and 8, 2. And it looks like that. What if I can put negative values into a cube root because it's an odd root. I just can't I can't put negative numbers into a square root. So if I put in -1, what cubed is -1? Well, -1, right? The cube root of -1 is -1. What's the cube root? We could do the same trick we did over here. What's the cube root of -8? In other words, what do I have to cube to get -8? Type it in chat. What do I have to cube? There we go, -2. Okay. I think you're unmuted, Madeline. There you go. Thanks. So -8, -2. And so there's another point. So I go -8, there's 5, 6, 7. So that's like right down about there. And it looks like this. Okay. And these are the points -8, -2, -1, -1. Okay. So there's my parent graph. We'll go a little quicker on this maybe. Would everybody agree that the domain here is going to be all reals, isn't it? Clearly, all the x values are taken care of on this. An ant can step on any possible x value. Okay, what about the range? Same thing, right? Because as the ant walks to the right forever, he's going to continue to go up, and as he walks to the left forever, he's going to continue to go down. So that's also all reals. Okay, what's the end behavior? As x approaches infinity, what is y approaching here? Noah? Okay, good. Infinity. As x approaches negative infinity, what is y approaching?
Negative infinity.
There you go. And this is pretty obviously continuous, isn't it? Okay, the reciprocal function. Finally, we get to one that mixes things up a little bit. This is a little different. So the reciprocal function, the parent graph, is just 1 over x. So let's make a t-table for this one. Okay, I can't put in 0, can I? Everybody see that? I can't divide by 0. So 0 is not in the domain. Okay, what happens if I put in a value like, how about if I put in a value, if I put 0 in, it blows up. It's undefined. Okay, but if I put in something like, what if I put in 1/2? What's the reciprocal? What's 1 over 1/2? What's 1 divided by 1/2? Everybody type that in chat. 1 over 1/2. Remember, if I have a fraction on the bottom, I just flip it and put it on top, right? So 1 over, okay, there you go. 1 over 1/2 gives me back 2, doesn't it? Right? What's that look like? 1 divided by 1/2. I just flip and multiply by the bottom. So this thing goes through the point 1/2, 2. What if I plug in the point 1? Well, 1 over 1 is just 1, right? So it goes through the point 1, 1. I'll write that one down. And what if I put in a value like 10? If I put in a value like 10, well, 1 over 10 is 1/10. So you can kind of see what's happening here, can't you? This thing is doing something like this. as I get smaller and smaller numbers closer to 0, 1 over those really small numbers is big. Like if I take something like 0.01 for x, 1 divided by 0.01 is 100. What if I take 0.0001? Well, 1 over 0.0001 is 10,000, right? So as I get closer and closer and closer to 0 on the x side, the y values are just getting huge, right? They're just exploding. If I put in really big numbers like a billion, well, 1 divided by 1 billion is a really small number. So we're getting extremely small outputs. They're still positive. They never quite get to 0, but the y values are getting closer and closer and closer to the x-axis as I go to the right. Okay, what about on the other side? It's going to be the same kind of thing, isn't it? If I plug in -1, I get an output of -1, right? So it's going to go through this point. Whoops. It's going to go through this point. If I put in a value like -1/10, well, 1 over -1/10 is -10. And so as I put in a really small negative number, I get a big negative output. So you can see it's doing the same kind of thing here, where it's just going to go like that. That's the picture. And the important points here are it goes through 1, 1, it goes through -1, -1. And even though this isn't a point on the graph, the point 0, 0 is kind of important, because that's like the point of symmetry, right? If I put a tack in this graph, I want to show you something. If I put a tack in this graph right at that purple point, and I spun this whole graph around 180 degrees, right? So if I just did that, it'd look the same, wouldn't it? Everybody agree it would line up exactly with where it started? So we call that rotational symmetry, right? So it's got this point of symmetry at 0, 0. So that's actually an important point, even though it's not on the graph. Okay, we need some other ways to describe this, though, because there's lots of strange stuff going on here. Oops. There we go. Well, let's start with the domain and the range. Okay, what's the domain of this thing? Well, are there any x values missing? Any x values that the ant could never stand on? Yeah, 0, right? The ant could never get to 0. If he walks from the left, he's going to go down forever, but he never gets to 0, right? If he's backing up from the right, he's going to get closer and closer and closer to 0, but the curve just deflects him up forever. He never can actually get there, right? So the domain is x is not equal to 0. Anything else is fair game, but it's never equal to 0. Same thing is true for y, right? The ant never actually gets to y equals 0. Whoops. So the range is y is never equal to 0. Okay. What about the end behavior? As x approaches infinity, what about this one? As the ant walks forever to the right, what y value is he approaching? He may never get there, but what y value is he approaching there, Grace? As x approaches infinity, what's the y value that we're approaching? You're right, Noah. What is it, Noah? Yeah, it's 0, isn't it? Right? As the ant moves to the right forever, his y values are getting smaller and smaller and smaller. And although they never actually get to 0, they approach that. This is like that example I use with the door, right? Imagine yourself in my room. If I start off like 2 meters in front of the door, and every second for the rest of eternity, I'm going to cut my distance to the door in half, right? So my steps get smaller. I never actually get to the door, right? But I'm always getting closer and closer to the door. The door is the only point I could ever identify that I don't actually get to, right? I could make a point between me and the door, and any point I make, I'm going to step on it or step over it or step on it, but I just never ever get to the door. So it's that same idea. As x approaches infinity, y approaches 0 but never gets there. As y approaches as x approaches negative infinity, the same thing happens, right? It's going to squeeze up against that x-axis but never get there. So y also approaches 0. Okay, is this continuous or discontinuous? Obviously, what do you think? Type it in chat, everybody. C for continuous, D for discontinuous. Yeah, it's discontinuous. I obviously have to pick my pen off the board, don't I? So this one is discontinuous. Okay, here's the key word. This is where we'll probably, well, we may get a little further than this. We may not finish this whole thing up today. Asymptotes. What are asymptotes? Okay, let's define that. Asymptotes are, I'm going to type this in because my pen's not working very well. So asymptotes are lines that a function approaches but never gets to. Okay, that's what an asymptote means. So are there any lines that this function approaches but never gets to? Well, yeah, the x-axis and the y-axis, right? Everybody agree? An ant walking along this function, he's going to get closer and closer and closer to the x-axis if he goes to the right forever or the left forever. And so one asymptote is the x-axis. So there's one asymptote right there, right? One asymptote is the line y equals 0, because that's the x-axis. Oops. Oh, come on. There we go. Right? Y equals 0. And y equals 0, remember, what is y equals 0? That's the same thing as the x-axis. Okay? What's another line that it never approaches? The y-axis, or that it never gets to. It approaches but never gets to. It bumps up against it from the left and the right, but never technically gets there, right? So here's another asymptote, is that y-axis right there, right? So what's the y-axis? That's the line x equals 0. That's the equation for the y-axis, okay? I'll put that right there for our notes. Okay, exponential function. An exponential function, that's going to be, there's a bunch of different ones we could do, but we're going to pick our parent graph for now to be 2 to the x. It could be some base other than 2 also, right? But we're going to pick base 2. That's a convenient one for us. Okay, so let's make a t-table first of all. So if I plug in, like, what if I plug in a value like negative 1? 2 to the negative 1, we haven't really reviewed this stuff, but if I have a negative exponent, so if I do something like 2 to the negative 1 power, that's the same thing. When I have a negative exponent, it just means it's positive on the bottom of the fraction. So that's the same thing as 1 over 2 to the positive 1. Okay, we'll review all that stuff later. So I get an answer of 1 over 2. Okay, so I can put a point at negative 1, positive 1/2. Okay, well, what if I put in a value? Let's pick like a really big negative value. Like, what if I put in a value like, negative 10? Well, that's the same thing as saying 2 to the negative 10 is the same thing as saying 1 over 2 to the 10th. Geez, 2 to the 10th would be, that'd be like 1 over 1024. That's a pretty small number, isn't it? Right? So what's it doing? As I go further and further to the left on my graph, the y values are getting smaller and smaller, right? So that looks like an asymptote, doesn't it? It's doing something like that. If I put in 1, well, 2 to the 1 is, or what if I put in 0? 2 to the 0, there's another rule of exponents that we will review. It's 1. Anything to the 0 power is equal to 1. And I know that's a little mysterious. We'll review that stuff later. But just for now, just believe me on that. So it's going to go through the point 0, 1. If I put in the number 1, 2 to the 1 is 2. You can kind of see what's happening then, can't you? This thing is going, it's just going to go through there, and it increases exponentially. It starts to increase faster and faster and faster. The really important point here is the one at 0, 1. Okay, and maybe this point right here too at 1, 2. That's really, if we plot those points, that gives us a pretty good idea what's going on. Okay, so what's the domain of this one? Everybody agree that if I were to project this onto the x-axis, all x values are okay, right? I could input any x value I want to. What about the range? Well, it's asymptotic here, right? If I go to the left forever, does the function ever get to the x-axis? Yes or no? In chat. It does not, does it, right? So it never actually gets to 0, but it approaches 0. So my range is going to be 0 to infinity, but I'm going to put in open parentheses, right? A parentheses by the 0, because it goes, that's the limit. That's the lower limit of the y values, but it never gets there. What about the end behavior? As x approaches infinity, as I go to the right forever, I'm going up forever. As x approaches negative infinity, what y value am I approaching? Type it in chat real quick. Okay. I'm not getting very many responses, but I got to hustle. So 0 is correct, right? The y value approaches 0. It is continuous, and I do have one asymptote, right? I have an asymptote on the x-axis. Okay, as I go to the left forever, it starts to hug that asymptote, but just never gets there. So I do have one asymptote, which is the x-axis, which is the line y equals 0. Okay, we almost got there. I'm going to let you guys go. We'll fill in that last little piece next time, but you can get going on the assignment that I'll put up. You can do all of the problems on the assignment except the one about logarithmic functions. We'll deal with that next time. All right, have a great weekend. I will be here after school if you need me. Otherwise, I will see you on Tuesday.